All right, here we go. So it's been a long break and time to get back to reality, and for reality for me that means work and scientific drinking. And what better way to get back to reality, or at least escape it, than using nukes in space? No, not that kind of nuke, this kind of nuke. And yes, they are two very different things. Cheers. All right, so tonight I'm drinking Against the Grain, the brown note. Yeah, it's good, but maybe not so much the can design. All right, so as you might notice, I'm kind of in the process of relocating my studio/office into this side room, so things are a little bit of a mess. Eventually, my new desk will go right there. But for now, this is what we got, and it's not too bad, at least not from your view, if you could see what I'm seeing. Yeah, there's stuff all over the place. So today we're going to be talking about nukes in space, specifically nuclear power in space, not nuclear bombs. And there are many variants of nuclear power in space, the most common probably being the radioisotope thermoelectric generator, or RTG for short. This has a long history of use both in NASA and other space agencies for projects such as the Voyager program, and even as much as today for use in the Curiosity and Perseverance rovers. It even has use in the near future for the Dragonfly mission, which is a nuclear-powered octocopter to explore the surface of Venus. Ever imagine that we'd be saying that seriously one day? It's nuts. It also has applications for manned space exploration, for power human colonies. We have to kind of keep it away from the soft, squishy bits that are the humans, but we'll talk more about that in a minute. Now, the RTG is kind of a low-power solution. Not meant to power entire bases, generally speaking, just small payloads for generally long periods of time. It's very reliable. It's good for use deep in the solar system when you're far away from the sun and don't get the same amount of solar flux that you get here at Earth or even at Mars. An RTG generates electricity by the decay of nuclear particles inside a closed container, which heat up the surrounding casing, which is then converted into electrical energy. That being said, when I say low power solution, they do last quite a bit. Of course, the power diminishes over time and eventually it asymptotically approaches zero. But it does so quite slowly. The Voyager spacecraft, for example, is still running on its RTG and still reporting back every once in a while. That's going on 44 years. That's a long lifetime for a mission. Another factor to consider with RTGs is that you have to position them away from the soft, sensitive instruments that are on the other end of the spacecraft. You can see this in Voyager and in other spacecraft configurations, and in the case of manned spaceflight, you have to keep it away from the humans, as I mentioned, away from the soft, squishy people. Now, we'll get into the dangers of space travel in another episode, but for now it's important that you keep in mind radioactive stuff on one end, humans on the other. We can keep them separate like this because radioactive objects follow the same inverse square law as many other things in our universe, such as electromagnetism, or light, or gravity, or even sound. That means that if you double the distance from something, it's 4 times weaker. Another option to protect people and sensitive scientific equipment from the radiation from an RTG or other nuclear power source is using a barrier of some kind, maybe something like lead or water, and we'll talk about that more in a minute. The next type of nuclear power is something we're all pretty familiar with here on Earth, at least in a conversational sense: nuclear power. That's fission, splitting large elements into 2 smaller elements. This works really well for heavy radioactive elements such as uranium or plutonium. And if you get enough of that together, you can create a runaway cascade, a chain reaction of splitting of atoms as those split away parts slam into other dense, large atoms and split them in part 2, and pretty soon you got this big glowing thing that we call an explosion. But that requires a very highly refined version of this radioactive material, such as uranium or plutonium. And most of the time, the stuff you dig out of the ground is just ore. It's not very refined at all. And if you refine that only to about 5 or 10%, that's the stuff you use for nuclear power. By having a less refined version, you decrease the chance of a runaway. In fact, you pretty much eliminate the chance of a runaway. However, if it's not controlled, it can get very hot, resulting in the melting of things around it. That's how we got the famous elephant's foot in Chernobyl. Since Chernobyl, however, the technology has improved, and the chances of having a runaway like that in a nuclear power plant is extremely, extremely low. And even in Chernobyl, a number of safety precautions had to have been violated for that to happen. But this episode isn't about nuclear power here on Earth. It's about nuclear power in space. And although I'd love to get into the nuance of nuclear power and the safety concerns and how it operates here on Earth, that's something I'll save for another time, and I'd love to get a tour of a nuclear plant to see how that works. The first thing you should know about nuclear power in space is that it takes an act of Congress to get it off the ground. No, really, it actually takes an act of Congress to launch a radioactive payload into orbit. And there are many reasons for that, not least of which if something happens to the rocket, you have a tremendous amount of fallout. And it costs a lot of time and money, usually about 6.5 years, to approve the process of launching a nuclear payload, along with the cost of $32 million that's associated with every launch just for contingency planning for radiological concerns, security concerns, and just logistics and planning. It takes a lot to launch a rocket to begin with, add a nuclear payload, and pretty much double the processing cost for that. Recent efforts have been made to try and streamline this process, partially because of future exploration missions on unmanned systems, and also because of our desire to get more manned space systems powered by things like RTG, and maybe manned missions powered by the next part, nuclear thermal rockets. Nuclear thermal rockets, or NTRs, have been around conceptually for quite a while. In fact, we actually had a test program going back in the 60s to try and develop this technology pretty quickly, and it's very promising. The idea behind nuclear thermal rocket, or NTR, is that you pass hydrogen through a nuclear thermal reaction or through the core to heat it up and accelerate those particles out at tremendous speeds out the back end of the vehicle. Now, this is still kind of throwing things out to go the other direction, Newton's second law, but it's a step in the right direction, and it's much more efficient than using traditional chemical propulsion. In fact, it can cut the transit time down between Earth and Mars to almost half the time. Now, there's some limitations on how you design your spacecraft when it's a nuclear thermal propulsion rocket, but we'll get to that in a minute. For now, let's talk about the final type of nuclear reaction, fusion. Now, don't expect fusion to get off the ground anytime soon. Now, we've seen fusion in place in things like Star Trek, but the running joke in the community is that fusion technology and fusion power is always 50 years away. It was 50 years away in 1960, and it kind of still feels like it's 50 years away as soon as 10 years ago. However, recent strides in the development of fusion technology might lead us into a more rapid progression and implementation of fusion technology. Now, there are many different experimental fusion configurations all around the world. There's ones in Germany, here in the US, and in China. But the one that's got everyone talking recently is K-STAR. K-STAR stands for Korea Superconducting Tokomak Advanced Reactor. Now, they were able to run their reactor for a staggering 20 seconds and generate power while they're doing it. Now, that's a lot, and it breaks their previous record at 8 seconds. Now, that may not sound like a lot, but in the world of fusion technology, that is a very long time. Now, opposed to fission, which again is the splitting of elements, fusion is the combining of elements to form a denser element. The most common process that happens in the universe, and what happens in our own sun, is the combination of hydrogen atoms into helium. Doing so releases tremendous amount of energy, and this isn't the same as just burning hydrogen gas like in the case of the Hindenburg. This is completely different. Normally, to fuse hydrogen into helium, it takes a lot of heat and a lot of pressure, something found at the core of our sun. To replicate this here on Earth, it takes a very strong electromagnetic field and very quickly moving hydrogen, specifically hydrogen plasma. That's what the Tokamak reactor does, and what K-STAR was able to do for 20 seconds. That being said, it's a very picky and precise process, and that's why it's been so hard to replicate in laboratory conditions. Your magnetic field has to be just right, the plasma flow has to be just right, and any variation thereof just causes it to fizzle out. And that's why it's been so hard to generate any reasonable time and maintain any generation of power for any fusion reactor on Earth. That's also why it's a lot safer than a nuclear reactor, at least the nuclear reactors we're used to, the fission reactors. Because if something goes wrong in the reactor, then just poof, it just shuts down, it goes away. There's no cascade, no runaway effect, no explosion, no meltdown, it's just poof. This reaction is so sensitive that the plasma can't even come in contact with air itself. So this reactor has to be evacuated of all air, produced in a vacuum. So considering all of the complexity and fine-tuning we have to do here on Earth, imagine doing that again in space. The bulky systems, the huge electromagnetics, the tremendous amount of power needed to generate the power to get the power out of it. It takes a lot of infrastructure and a lot of manpower. So don't expect to see fission in space anytime within our lifetimes. But you never know. We could be surprised, maybe when I'm very old and gray. All right, so now let's get into the meat and potatoes of the matter. Nuclear-powered spacecraft design. It would be hard to talk about nuclear-powered spacecraft without at least mentioning the Orion project. No, not that Orion, this Orion. This was the Orion that was conceived of in the 1950s as a post-war atomic-era glory age exploration of space, where it just solved the problem of space travel by chucking out nukes out the back end and blowing them up, using a big blast shield to absorb the shockwave from the nuclear blast and power the spacecraft onward. The concept was that if you could detonate enough nuclear bombs, you could accelerate to pretty much any speed you wanted to, depending on how much you wanted to carry. Never mind the fact that you would destroy all the Earth infrastructure as you depart. Yeah, minor details, right? I don't think I really need to get into the details about why this is such an impractical idea, but at least I mentioned it, right? More practically, the nuclear thermal rocket idea that I mentioned earlier is on the horizon, and we might see that sooner than you might think. But first, let's talk about configurations involving an RTG. Like I mentioned, RTG and other nuclear propulsion sources are especially appealing when you want to go much further beyond Earth or Mars, as the solar flux drops off exponentially. In a practical sense, the nuclear thermal rocket that I mentioned earlier is a clear route forward in the near future, just like the RTGs were before. Now, there are rules that apply to spacecraft design when including either of these nuclear reactors, and that is, keep the scientific instruments and the squishy bits, like humans, on the opposite side of the rocket as the nuclear bits. Using nuclear power is a viable option for both solar electric propulsion and nuclear propulsion as well, depending on how much power and resources you want to dump into the reaction and how big your spacecraft is. However, NTR seems like the natural choice. It's much faster. And although it isn't as efficient as something like an electric propulsion system, it can get you there much, much quicker. Here you can see the Voyager spacecraft, where the RTG is positioned opposite of a lot of the sensitive equipment. The same is true here on the Curiosity rover, with the RTG sticking out the back end and all the sensitive scientific instruments there on the front. For manned spacecraft design, it doesn't get too much different. You put the nuclear reaction in the back, the nuclear thermal rocket, then you have the storage tanks and the manned spacecraft portion at the very nose of the vehicle. This allows whatever's in the storage container to buffer some of that radioactivity as it crosses through into the manned section. An intuitive insulator against radioactive decay would be things like lead or heavy materials, concrete, things that are big, heavy, and burly, but a clever alternative is water, and since water is something we need in space anyway, to split into hydrogen and oxygen for breathing and propulsion, or just to drink, it's an intuitive choice to place between you and this radioactive source at the back of your spacecraft. Additionally, long-term space voyages would need to have a storm shelter, a place to go whenever there's a solar storm that generates a lot more radioactivity than usual. And of course, in the vacuum of space, there's no protection against that radioactivity on its own. So this storm shelter should intuitively be placed towards the rear of the manned portion of your spacecraft to act as an additional layer of insulation between you and your radioactive thruster. As is the case with any spacecraft, there are additional constraints placed on its design, one thing being, of course, the size of the rocket that can deliver it into orbit. Once Starship comes around, this may be less of a problem. However, in the meantime, SLS is the largest rocket available to us, soon to launch later this year. Fingers crossed. Nevertheless, the physics remains the same, and you still have the radioactive bit in the back and the squishy bits in the front. Currently, the nuclear thermal rocket has received a renewed wave of interest from the military and academic community. Both NASA and the DoD have expressed interest in further developing the nuclear thermal rocket, or NTR, as a means of space propulsion. At first, the interest was shown in the form of $125 million of investment from NASA in 2019, continued investment in 2020, and from the Department of Defense through the US Space Force, which provided $12 million in funding through DARPA to Griffin Technologies, which is said to perform an on-orbit demonstration of the nuclear thermal propulsion technology. Either way, the future seems bright for this technology and others, although fusion is still, as always, 50 years away. My name is Mas, and thanks for watching. Cheers.